All right, let's look into something a bit more complicated. Now, unfortunately, this equation, these 58 and 57 should really be considered at once, but that's not possible owing to the page layout. Okay, so we're going to take our seal keys, right? That's the seal keys for this epoch. We're going to reference our time, current time, into the seal keys. And we're going to, this won't work, of course, because the seal keys are going to be at most, they're going to be at most 600 seal keys. That's the size of the epoch. And yet our time is going to be however many 6-second periods have elapsed since the start of 2024, a lot, which is why we use this notation here, and it just means modulo. We're going to dereference, we're going to index into a sequence modulo the length of the sequence. Yeah. In this case, we know this sequence is 600, so the modulo will be 600. So it's our time modulo 600. This is just a shorthand for that. And this gives us I, which is our block's seal key. And we're looking for an authorization. We're looking to make sure that the block seal is in line with this key, is in line with what we're expecting, this like privilege. Now, our seal keys might be either tickets from the lottery, that's the regular, that's what it should be under regular operation, or in fallback, there'll be Bandersnatch keys. It's going to be one or the other. Let's consider the regular possibility first. Firstly, capital T, this is a marker that we use later. We're going to set that to 1. We actually set it to 0 if it's a fallback. This is just for us to know whether we're dealing with a fallback or regular operation. Now we take a look at the seal, the block seal, HS, and we pass it through the VRF output function, calligraphic Y. This gives us the output of the VRF. And we make sure that the ticket's identity, I subscript Y, is equal to that. Basically, we're looking to make sure that the seal of the block, this authorizing seal, is correct. That it results in the correct ticket identity. If it doesn't, it means a validator is not allowed to produce this block because they have not proven that they actually own the ticket, that they control the key behind the ticket. So that's what this bit means. We require the seal to be a signature, a Bandersnatch signature as it happens, on the unsigned encoding of the header. So that's the sort of message. For the supposed, the authority, the author of the block, HA, this is the author's key, right? If you remember, we had HK and HA. HK is the index into the current validator set. HA is the key that index represents. And then this is the interesting bit. So this is the VRF input. This is the sort of string of data that we put in that is not biasable by the, well, is not so biasable by the block author. It's basically a bit of text, XT. This is just a bit of hygiene text to make sure the different parts of JAM don't end up requiring signatures with the same or VRFs with the same input. It also includes some entropy, eta prime 3, and the ticket ID. Sorry, not ticket ID. The entry index, 0 or 1. Yeah. This entry index just makes sure that it will generate a different VRF for the different entries. Yeah. If it weren't here, then both of their entries would always generate the same ticket, right? And that would be pretty useless. The entropy is there so that they can't, it helps avoid them being able to select a key that they know will generate a good ticket. Because they don't know this entropy until the lottery is already, until they've already committed to their key. Good. So let's look at the Bandersnatch case. This is the fallback case, remember. This is if the lottery doesn't complete correctly. The only way that the lottery isn't going to complete correctly is if there were just no blocks produced in the last, I don't know, few hundred, like the last half hour. It's highly, highly unlikely to happen. And if it's happening, we've probably got other things to worry about than this using Bandersnatch keys rather than anonymous tickets. Good. So in this case, we require I, which is the Bandersnatch key of the validator, to just be the same as the author of the block. Yeah, pretty simple thing there. And we require the seal to, again, this is more or less the same, right? So we require the seal. It has to be signed by the author of the block. It has to be on the unsealed encoding of the header. In this case, this seal VRF takes as input a different string and the entropy. It's missing the ticket entry term because it's not a ticket, right? It's just their signature. Good. So that is the seal signature. That's everything you need to know about correctly verifying whether the block whether it's allowed, whether it's authorized. Let's look at the VRF. This is our entropy VRF. So that entropy VRF is another signature. We're not signing anything in particular. So that's why this term is empty. We're not like, I don't know, committing ourselves to some particular thing, some particular message. It must be signed by us. And our VRF input, again, we've got this string here, that's again just for hygiene, together with the VRF output from our previous, from our seal, right? So we're kind of using the seal's VRF output as the entropy's VRF input. And this helps us get to the point where it's really, really hard for a validator to bias the entropy that they're feeding into the entropy accumulator. Like really, really hard. Basically, we're now at a point where the validator can only bias it in one way, and that's by not producing a block. And if they don't produce a block, there's another validator who presumably they don't know that will put more entropy in and bias it in some, well, not bias it, but change it in some way that they can't predict. Which means that it's not really in their interest to not put any entropy in. They should just put their entropy in and get a block reward. Good. Those are the two seals. Next up, eta. Eta is 4 hashes. Right? First one is our accumulator, eta 0. And eta prime 0, so the new value of the accumulator, is the hash of the old value of the accumulator along with the VRF output from our entropy VRF. Yep, pretty straightforward. The other 3, we move them along if it's the new epoch, otherwise we'll leave them alone. Right? So they just kind of get shunted along epoch to epoch. So at the beginning of the next epoch, the previous epoch's entropy accumulator becomes the historical eta 1, the first historical value. Eta 2 takes the old eta 1, eta 3 takes the old eta 2, and the old eta 3 gets discarded. And for what it's worth, eta 0 is left alone. The entropy just is set there, and it just accumulates into the old value of eta 0. We don't bother like resetting it to zeros or anything like this. Right.